In this video, we're going to apply the method of Lagrange multipliers to find the optimums of a constrained optimization problem. We're going to write this out in quite a mathematical form. We have a function that we want to optimize, f of xy, and it has a relatively complicated formula here. And we're going to subject that to the constraint, so a limitation on the xy's we can pick. And we can see that we would need that because looking at this function here, if we have x and y squared, they're going to be the most important terms in this whole thing. If we chose to let x and y get really, really big, we can make this function as big as we want. However, if we limit ourselves only to x plus y equals 10 values, then we can feel there's going to be a trade-off, some balance between the x's and y's that we pick that make this as large as possible. We're going to approach this problem in both a graphical and a formula-based approach to see how those two elements combine or fit together. The first thing we're going to do then is look at the graphical meaning of the constraint. So x plus y equals 10 is our constraint. And in the formulation for Lagrange multipliers, this matches our function of x and y on one side equals a value k on the other. This type of constraint is often called a budget constraint because it has the form of I can spend this much money plus this much money, say food and housing, and I have a maximum amount of money I can spend. So those things adding up to a total equals a budget is a pretty common way to think about that form of equation for the constraint. Now, that's not technically true here, they're just x plus y's, but we'll see this form quite frequently. But what about the graphical meaning? If we're looking at the set of points that satisfy this equation, as we've seen with contours, it's often easier to see the graph or see the function if it's written out in a more traditional way. So putting y on one side and being careful, it'll be 10 minus x, bringing the x to the other side. That is a line with slope -1 and y equals 10 intercept. So out of all the points we can pick, let's go 1, 2, 3, 4, 5. Out of all the points we can pick, this set of points along this line is our constraint x plus y equals 10. We can choose any values we want along here. We can't choose values here because they don't satisfy that requirement. Now our overlay on top of that is, well, as we drive along this road, again, that's an easy way to visualize this as a road on a map, we're going to hit different elevations. We're going to be going up and then maybe down, maybe up. We don't know how that relates until we bring in the formula for the function f. Our next step is to see how the Lagrange multiplier equations will help us find the highest point or lowest point along this road, given the formulas for f and the constraint. Our next step is to move into the formulas. We want to write down the three equations obtained by the method of Lagrange multipliers. And those start with the gradient of f is equal to lambda times the gradient of g. And this whole element here can be remembered as the gradient of f is parallel to the gradient of g at maxes and mins. The other constraint is the constraint itself, g of xy equals k. That was the equation we were given as part of the problem. We have to satisfy that. Our next step then is to break this into pieces that are more easily solved. The gradients are vectors. We don't usually deal with vector equations very well, so let's break it down into components. And if we do that, the components of the gradient of f are the x component and the y component, and those have to equal a lambda times the same component in g, so gx, and the lambda times gy, and then our constraint comes along for the ride one more time, and this gives us at the same point 3 equations and 3 unknowns. You should be able to feel that kind of relationship in the math when you get to this stage. What we're then going to do is translate that into the context of our particular problem. So our function was f of xy equals, going back a page, x minus 10y plus the x squared plus y squared all over 20. And our x plus y equals 10 was our constraint, and that was our g of x, y, and our k. So our next step is then to implement the derivative calculations. We need to fill in all the blanks for this. In particular, we need to know what the x partial derivative is. Scan across, we get 1, 0, and then these are actually two separate terms. If it helps, we can write this as two separate terms in a sum. So when we take the x derivative, we simply get x over 10, or 2x over 20. For the y derivative, we're going to get negative 10 plus 0 plus 2y over 20, or y over 10. Then we do the same calculation here, and this turns out to be quite simple. The x derivative is just 1, and then when we take the y derivative, we simply get 1 as well. Looking at our equations here, we now have all the ingredients we need. So we're going to put those together. 1 plus x over 10 is going to be a multiple of the x derivative of g, that's 1. And for the y derivative, the same thing. The y derivative of f is a multiple of the y derivative of g, which is 1. And our last constraint is simply the x plus y equals 10. And so we typically number those equations, 1, 2, and 3, and that helps us solve for all the variables that we need. We'll do that on the next page, copying over this set of equations to get us started. At this point, you can use any solving approach that you like, as long as it follows all the rules for manipulating equations. What is nice here is that we actually have a lambda and a lambda on both sides here, so we can actually set the equations 1 and 2 equal to one another. And that gives us 1 plus x over 10 is equal to lambda, but lambda is also equal to negative 10 plus y over 10. Moving that around, we would get, bring this over here, we'd have 11 equals y over 10 minus x over 10. So that gives us a new equation that we might be able to combine with our constraint here. In fact, looking at an alternate form here, we could say from equation 3 that y equals 10 minus x. So what we can do is sub that in for y, and we'll have 11 equals 10 minus x all over 10 minus x over 10. Now we have one equation with one x in it. We can solve for x. Let's multiply through by 10. That gives us 110. And minus x, that's 110 equals 10 minus 2x. Bring that over. Actually, let's bring the x over. We have 2x equals 10 minus 110. That'll be negative 100. So there's one point that satisfies Lagrange equations, and it is x equals negative 50. We can then sub that into 3. We can use any equation we like, but 3 has a nice simple form to it. The y value that matches that is going to be 10 minus 50, and that is positive 60. So the point negative 50, 60 is the only solution to the Lagrange equations. Lagrange multiplier equations. And so it's our candidate, our only candidate, for a max or a minimum along that constraint curve. We can study the result of our calculations graphically as well, recalling that this line here is our constraint line, x plus y equals 10, or written more traditionally in slope-intercept form, y equals 10 minus x. This is the road that we can travel on, and we can see that we are crossing different contours. So imagine we're here. As we're crossing contours, we're changing heights. The point that we found at negative 50, 60 is right here. And you can see there's an interesting relationship between the contours of our function and the road we're allowed to drive on, or the constraint. We can see it more clearly when we zoom in over here. As we're driving, as we're moving along this contour, we can see that we're at height negative 330, 335, so this is downhill in this direction. And as we move along this line, we can see that we're going from 335 to negative 340, and we just touch 345, and that's right actually here. This location is our point negative 50, 60, and we see that we're going down as we reach this point here, and then we can never get any lower than that. We never reach 350 or 355 negatives. We end up simply continuing along the road if we stay on that constraint, and we end up going up afterwards. So this confirms that the point that we found is an exceptional point in the sense that it's the lowest possible value we can reach as we traverse this constraint or this road, and we can also validate our idea of the gradient vectors being perpendicular. If we look back at this diagram for a second, if we drew a perpendicular line to the function contours, and we then drew a perpendicular line to the constraint, they are not aligned in any particular way. Whereas when we're at this point here, if you follow the red line, it goes right into here, and if it's pointing uphill, it would point in this direction. And on a black line, we would have a perpendicular vector as well. It'll point in exactly the same direction. Might point the other way, we don't know, but it's enough to know that they are parallel to each other, these two vectors, and that is what we used to create the equations that let us identify this point purely through working with the formulas. So we get a beautiful confirmation about the gradient information here that validates what we found through the formula calculations.